Today we'll be talking about unrecoverable errors with panic. Sometimes bad things happen in your code and there's nothing you can do about it. In these cases, Rust has the panic macro. There are two ways to cause a panic in practice: by taking an action that causes our code to panic, such as accessing an array past the end, or by explicitly calling the panic macro. In both cases, we cause a panic in our program. By default, this panic will print a failure message: unwind, clean up the stack, and quit. Via an environment variable, you can also have Rust display the call stack when a panic occurs to make it easier to track down the source of the pain. Unwinding the stack or aborting in response to a panic. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up to the stack and cleans up the data from each function it encounters. However, this walking back and cleaning up is a lot of work. Rust therefore allows you to choose the alternative of immediately aborting, which ends the program without cleaning up. Memory that the program was using will then need to be cleaned up by the operating system. If in your project you need to make the resulting binary as small as possible, you can switch from unwinding to aborting upon a panic by adding panic equal to abort to the appropriate profile sections in your cargo.toml file. For example, if you want to abort on a panic in release mode, add this. Let's try calling panic in a simple program. When you run the program, you will see something like this. The call to panic causes the error message contained in the last two lines. The first line shows our panic message and the place in our resource code where the panic occurred indicates that it's the second line, fifth character of our src main.rs file. In this case, the line indicated is a part of our code, and if we go back to that line, we see the panic macro call. In other cases, the panic call might be in code that our code calls, and the file name and the line number reported by the error message will be someone else's code, where the panic macro is called, not the line of our code that eventually led to the panic call. We can use the back trace of the functions the panic call came from to figure out the part of our code that is causing the problem. We will discuss back traces in more detail next using a panic backtrace. Let's look at another example to see what it's like when a panic call occurs from a library because of a bug in our code. Instead of from our code calling the macro directly. Listing 9.1 has some code that attempts to access an index in a vector beyond the range of valid index. Here we are attempting to access the 100th index of our vector, which is at index 99, because indexing starts at the 0, but the vector has only 3 elements. In this situation, Rust will panic. Using a square bracket is supposed to return an element, but if you pass an invalid index, there is no element that Rust could return here that would be correct. In C, attempting to read beyond the end of a data structure is undefined behavior. You might get whatever is at the location in memory that would correspond to that element in the data structure, even though the memory doesn't belong to that data structure. This is called as buffer overread and can lead to security vulnerabilities. If an attacker is able to manipulate the index in such a way as to read the data, they shouldn't be allowed to that is stored after the data structure. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. This error points at line 4 of our main.rs, where we attempt to access index 99. The next note line tells us we can set the rust underscore backtrace environment variable to get a backtrace of exactly what happened to cause the error. A backtrace is a list of all the functions that have been called to get to this point. Backtraces in Rust works as they do in other languages. The key to reading the backtrace is to start from the top and read until you see files you wrote. That's the spot where the problem that called your code. This before and after line might include core Rust code, standard library code, or crates that you are using. Let's try getting a backtrace by setting the rust underscore backtrace environment variable to any value except 0. Listing 9-2 shows output similar to what you will see. That's a lot of output. The exact output you see might be might be different depending on your operating system and Rust version. In order to get back traces with this information, debug symbol must be enabled. Debug symbols are enabled by default when using cargo build or cargo run without the release flag. As we have here in the output of listing 9-2, the line 6 of the backtrace points to the line in our project that causing the problem. Line 4 of src main rs. If we don't want our program to panic, we should start our investigation at the location pointed to by the first line mentioning a file we wrote, and listing 9-1 where we deliberately wrote code that would panic. The way to fix the panic is to not request an element beyond the range of the vector indices. When your code panics in the future, you will need to figure out what action the code is taking with what values to cause the panic and what the code should do instead. We will come back to panic and when we should and should not use panic to handle error conditions in the to panic or not to panic section later in this chapter. Next, we will look at how to recover from an error using result. Most errors aren't serious enough to require the program to stop entirely. Sometimes when a function fails, it's for a reason that you can easily interpret or respond to. For example, if you try to open a file and that operation fails because the file doesn't exist, you might want to create the file instead of terminating the process. Recall from handling potential failure with result in chapter 2 that the result enum is defined as having two variants, OK and error, as follows. The T and E are generic type parameter. We will discuss generics in more details in chapter 10. What you need to know right now is that T represents the type of the value that will return in a success within the OK variant, and E represents the type of the error that will be written in a failure case within the error variant. Because the result has the generic type parameter, we can use the result type and the function defined on it in many different situations where the successful value and the error value we want to return may differ. Let's call a function that returns a return value because the function could fail. In listing 9-3, we try to open a file. The return type of file open is a result type. The generic parameter T has been filled in by the implementation of file open with the type of the success value, which is a file handle. The type of E used in the error is standard IO error. This return type means the call to file open might succeed and return a file handle that we can read from or write to. The function call also might fail. For example, the file might not exist or we might not have permission to access the file. The file open function needs to have a way to tell us whether it succeeded or failed, and at the same time give us either the file handle or error information. This information is exactly what the result enum conveys. In case where the file open succeeds, the value in the variable greeting file result will be an instance of OK that contains a file handle. In the case where it fails, the value in greeting file result will be an instance of error that contains more information about the kind of error that happened. We need to add the code in listing 9-3 to take different action depending on the value file open returns. Listing 9-4 shows one way to handle the result using basic tool, the match expression that we discussed in chapter 6. Greeting file result. Note that the option enum note that like the option enum, the result enum and its variant have been brought into scope by the prelude, so we don't need to specify the result : before the OK and ERR variants in the match arms. When the result is OK, the code will return the inner file value out of the OK variant, and we then assign the file handle value to the variable greeting file. After the match, we can use the file handle for reading or writing the other arm of the match. Handles the case where we get an error value from the file open. In this example, we have chosen to call the panic macro if there is no file named hello.txt in our current directory. and we run this code, we'll see the following output from the panic macro. Matching on different errors, the code in listing 9-4 will panic no matter why file open failed. However, we want to take different actions for different failure reasons. If file open failed because the file doesn't exist, we want to create the file and return the handle to the new file. If file colon open failed for any other reason, for example because we didn't have permission to open the file, we still want the code to panic in the same way as it did in listing 9-4. For this, we add an inner match expression shown in listing 9-5. The type of the value that file colon open returns inside the error variant is IO error, which is struct provided by the standard library. This struct has a method kind that we can call to get an IO error kind value. The enum IO error kind is provided by the standard library and has variants representing the different kind of errors that might result from an IO operation. The variant we want to use is error kind colon not found, which indicates the file we are trying to open doesn't exist yet. So we match on greeting file result, but we also have an inner match on error kind. The condition we want to check in the inner match is whether the value returned by error kind is the not found variant of the error kind enum. If it is, we try to create the file with file colon create. However, because file colon create could also fail, we need a second arm in the inner match expression. When the file can't be created, a different error message is printed. The second arm of the outer match stays the same, so the program panics on any error besides the missing file error. Alternative to using match with result TE, that's a lot of match. The match expression is very useful but also very much a primitive. In chapter 13 you will learn about closure, which are used with many of the methods defined on result TE. These methods can be more concise than using match when handling result TE values in your code. For example, here's another way to write the same logic as shown in listing 9-5, this time using closures and the unwrap or else method. Although this code has the same behavior, it doesn't contain any match expression and is cleaner to read. Shortcut for panic on error: unwrap and expect. Using match works well enough, but it can be a bit verbose and doesn't always communicate intent well. The result type has many helper methods defined on it to do various more specific tasks. The unwrap method is a shorthand method implemented like the match expression we wrote in listing 9-4. If the result value is OK variant, unwrap will return the value inside the OK. If the result is error variant, unwrap will call the panic macro for us. Here is an example of unwrap. If we run this code without a hello text file, we will see an error message from panic call that the unwrap method makes. Similarly, the expect method lets us also choose the panic error message using expect instead of unwrap, and providing good error message can convey your intent and make tracking down the source of panic easier. The syntax of expect looks like this. We use expect in the same way as unwrap to return the file handle or call the panic macro. The error message used by expect when it's called to panic will be the parameter that we pass to expect rather than the default panic message that unwrap uses. Here's what it looks like in production quality code. Most station choose expect rather than unwrap. That way, if your assumption are ever proven wrong, you have more information to use in debugging. Propagating error. When a function's implementation calls something that might fail, instead of handling the error within the function itself, you can return the error to the calling code so that it can decide what to do. This is known as propagating the error and gives more control to the calling code, where there might be more information or logic that dictates how the error should be handled than what you have available in the context of your code. For example, listing 9-6 choose a function that reads a username from a file. If the file doesn't exist or can't be read, the function will return those errors to the code that called the function. The function can be written in a much shorter way, but we are going to start by doing a lot of it manually in order to explore error handling. At the end, we will show the shorter way. Let's look at the return type of the function first. This means the function is returning a value of the type where the generic parameter t has been filled in with the concrete type string and the generic type e has been filled in with the concrete type IOError. If this function succeeds without any problem, the code that calls this function will receive an OK value that holds a string, the username that this function read from the file. If this function encounters any problem, the calling code will receive an error value that holds an instance of IOError that contains more information about what the problems were. We choose IOError as the return type of this function because that happens to be the type of the error value written from both of the operations we are calling in this function's body that might fail: the file open function and the read to string method. The body of the function starts by calling the file open function, then we handle the result value with a match similar to the match in listing 9-4. If the file open succeeds, the file handle in the pattern variable file becomes a value in the mutable variable username file, and the function continues. In the error case, instead of calling panic, we use return keyword to return early out of the function entirely and pass the error value from file open now in the pattern variable e back to the calling code as this function's error value. So if we have a file handle in user name underscore file, this function then creates a new string in variable username and calls the read to string method on the file handle in the username underscore file to read the contents of the file into username. The read to string method also returns a result because it might fail even though the file colon open succeeds. So we need another match to handle the result. If read to string succeeds, then our function has succeeded and we return the username from the file. That's now in username wrapped in an OK. If read to string fails, we return the error value in the same way that we have written error value in the match that handle the return value of file open. However, we don't need to explicitly say return because this is the last expression in that function. The code that calls this code will then handle getting either an OK value that contains a username or an error value that contains an IO error. It's up to the calling code to decide what to do with those values. If the calling code gets an error value, it could call panic and crash the program. Use a default username or look up to the username from somewhere other than the file name. For example, we don't have enough information on what the calling code is actually trying to do. So we propagate all the success or error information upward for it to handle appropriately. This pattern of propagating error is so common in Rust that Rust provides a question mark operator to make this easier. A shortcut for propagating error is the question mark operator. The question mark placed after result value is defined to work in almost the same case as match expression. Defined to handle the result value in listing 9-6. If the value of the result is an OK, the value inside the OK will get returned from this expression, and the program will continue. If the value of the error will be returned from the whole function, as if we had to return the return keyword, so the error value gets propagated to the calling code. There is a difference between the match expression from listing 9-6 does and what the question mark operator does. Error values that have the question mark operator called on them go through the from function depend in the from trait in the standard library, which is used to convert values from one type into another. When the question mark operator calls the from function, the error type received is converted into the error type defined in the return type of the current function. This is useful when the function returns one error type to represent all the ways a function might fail, even if parts might fail for many different reasons. For example, we could change the read username from file function in listing 9-7 to return a custom error type name our error that we define. If we also define impl from error for our error to construct an instance of our error from an IO error, then the question mark operator calls in the body of read username from file will call from and convert the error types without needing to add any more code to the function. In the context of listing 9-7, the question mark operator at the end of file open call will return the value inside an OK to the variable username file. If the error occurs, the question mark operator will return early out of the whole function and give an error value to the calling code. The same thing applies to the question mark at the end of the read to string call. The question mark operator eliminates a lot of boilerplate and make this function's implementation simpler. We could have even shorten this code further by chaining method calls immediately after the question mark as shown in listing 9-8. If an read user from file we have moved the creation of the new string in username to the beginning of the function. That part hasn't changed. Instead of creating a variable username underscore file, we have changed the call to read to string directly onto the result of file open. We still have the question mark at the end of the result of the read to string call, and we still return an OK value containing username when both file colon open and read to string succeed rather than returning errors. The functionality is again the same as in listing 9-6 and 9-7. This is just different, more ergonomic way to write it. Reading a file into string is fairly common operation, so the standard library provides a convenient fs colon read to string function that opens the file, creates a new string, and reads the contents of the file, puts the content into that string and returns it, of course using fs colon read to string doesn't give us the opportunity to explain all the error handling, so we did the longer way first, where the question mark operator can be used. The question mark operator can only be used in function whose return type is incompatible with the value the question mark is used on. This is because question mark operator is defined to perform an early return of value out of the function in the same manner as the match expression we defined listing 9-6. In listing 9-6, the match was using a result value, and the early return arm returned an error value. The return type of the function has to be a result so that it's compatible with this return. In listing 9-10, let's look at the error we will get if we use the question mark operator in a main function with a return type incompatible with the type of value we use question mark on. This code opens a file which might fail. The question mark operator follows the result value returned by file open, but this main function has the return type of rounded bracket not result. When we compile this code, we get the following error message. This error points out that we are only allowed to use the question mark operator in a function that returns result, comma, option or another type that implements from residual. To fix the error, you have two choices. One choice is to change the return type of your function to be compatible with the value you are using the question mark operator on, as long as you have no restriction preventing that. The other technique is to use a match or one of the result type methods to handle the result in whatever way is appropriate. The error message also mentioned that question mark can be used with option values as well as with using question mark on result. You can only use question mark on option in a function that returns an option. The behavior of the question mark operator when called on an option is similar behavior when called on result. If the value is none, then none will be written early from the function at that point. If the value is sum, the value inside the sum is the resulting value of the expression and the function continues. Listing 9-level has an example of a function that finds the last character of the first line in the given text. The function returns option car because it's possible that there is a character there, but it's also possible that there isn't. This code takes the text string slice argument and calls the line method on it, which returns an iterator over the lines in the string. Because this function wants to examine the first line, it calls next on to the iterator or to get the first value from the iterator. If the text is the empty string, this call to next will return none, in which case we use question mark to stop and return none from the last char of first value. If text is not the empty string, next will return some value containing a string slice of the first line in text. The question mark extracts the string slice and we can call car on the string slice to get iterator of its character. We are interested in the last character in this first line, and so we call last to return the last item in the iterator. This is an option because it's possible that the first line in this is the empty string. For example, if text starts with a blank line but has characters on other line as in. However, if there is a last character on the first line, it will be written in the same variant. The question mark operator in the middle gives us a concise choice to express this logic, allowing us to implement the function in one line. If we couldn't use the question mark operator on an option, we would have to implement this logic using more method calls or a match expression. Note that you can use the question mark operator on a result in a function that returns the result, and you can use the question mark operator on an option in a function that returns option, but you can't mix and match. The question mark operator won't automatically convert a result to an option or vice versa. In those cases, you can use methods like the OK method on a result or the OKOR method on option to do the conversion explicitly. So far, all the main function we have used return rounded bracket. The main function is special because it's the entry and exit point of executable program, and there are restrictions on what its return type can be for the program to behave as expected. Luckily, main can also return a return. Listing 9-12 has the code from listing 9-10, but we have changed the return type of main to be result. Box dynamic and added a return value OK to the end. This code will now compile. Box dynamic error type is a trait object, which we will talk about using the trait objects that allow for values of different kinds section in chapter 17. For now, you can read the box dynamic error to mean any kind of error using question mark on a result value in a main function with the error type. Box dynamic error is allowed because it allows any error value to be returned early, even though the body of this main function will only ever return errors of uh, type standard error. By specifying box dynamic error, this signature will continue to be correct even if more code that returns other error is added to the body of main. When a main function returns a result, the executable will exit with a value of 0 if main returns OK, and will exit with a non-zero value if main returns an error value. Executable returns in C returns integer type when they exit. Programs that exit successfully return the integer 0, and program that error returns some integer other than 0. Rust also returns integer from executable. To be compatible with this convention, the main function may return any type that implement the standard process termination thread, which contain function report that returns an exit code. Consult the standard library documentation for more information on implementing the termination thread for your own types. Now that we have discussed the details of calling panic or returning result, let's return to the topic of how to decide which is appropriate to use in which cases.